All right. So we're going to start constructing confidence intervals. So this is a confidence interval for a population variance, so your sigma squared, or a standard deviation, so just your sigma. So let S squared be the sample variance from a simple random sample of size n from a normal population. Let 100 times 1 minus alpha be your confidence level for your confidence interval for a population variance of sigma squared. So what we'll do here is we are going to have n minus 1 times sigma divided by your chi squared. So what you're going to do is you're going to put, so if it was like a 95% confidence interval, this would be your chi of 0.05 down here, and then this would be the chi, not 0.5, sorry, 0.25 here, and this would be the chi squared for the 0.095 here. So the reason we're doing that is because your largest score is going to be down here, making that a smaller number on the side. Now, if we wanted to have the standard deviation instead, well then, just like with this, if I wanted to take a variance, all I'd do is do a square root to get my standard deviation. Well, I just do a square root of everything and I get the confidence interval for my standard deviation. So with this section, it likes to force you to go back to some older stuff here. The compressive strength of several concrete blocks in pounds per square inch are measured in the following results, which we all see right here. So those are the different strengths. Assume these values are simple random sample from a normal population. We want to construct a 95% confidence interval for the population standard deviation. So what we need to do is we need to just record a little bit of information here. So because they give us a list of values, that means we have to go back and calculate a variance ourselves. And we're doing a standard population standard deviation. Okay, so we're only doing standard deviation. Just want to make sure I have the right thing here. Okay, so you have to be a little careful when you're doing this, that you're using the right numbers in the right way. Okay, so what we need to do is we need to go back to our TI-84, and we're going to have to enter this data in to figure out what we're looking for. And just to go back here for a second, remember that what we're using here is S squared. So we need variance. We don't need standard deviation. In both cases, what we need is variance if we want to calculate this correctly. So we'll do what we always have done is we take our data, we go to second. Oops, sorry, not second, not yet. We go to stats, we go to edit, and we just put that data in the list. So 1989.9, 1993.8. And I'm going to pause this a second and enter the rest of the data so you don't have to sit here and watch me do it. Okay, so there's all the data that was over here on the side entered in. So you could just go to one of our statistics, but just remember that this number that you get here, this S, that is your standard deviation. You need to square that if you want variance. So we would have to take that 51960222288 and square it. So this is one option for you, and I'll show you another option here in a second. So this one, you want to make sure that you do take as much of the number as you can, because if you take as many decimals as you can. Sorry, I was trying to get it in here and square it, just so we can avoid any kind of rounding error. But you do have another option around this. So if you go to second stat, it takes you over here in the list. And if you go over, so this is where you can sort lists and other things, but you go over to math, you see you have min, max, mean, median, sum, product, standard deviation, variance. So we go to 8 and go to variance, then we just do second L1 to make sure that's the list that goes in there, close parentheses, enter. And as you see, it's going to give you that variance as well. So that's another way of doing it. So you don't have to find standard deviation, square it. You can just simply go get that variance. Okay. So like I said, remember, you need the variance, not the standard deviation, even if we are finding the confidence interval for a standard deviation. Okay, so before we go do anything more, we also need to have those chi-squared scores. So we have a sample size of 1, 2, 3, 4, 5, 6, 7. So my sample size is 7. So that means my degrees of freedom are 6. Now we're doing a 95% confidence interval. So that means that alpha is going to be 1 minus 0.95. So that's going to be 0.05. So alpha divided by 2 is 0.025. So we got one chi-square score that we have to find that's just going to be that chi-squared of alpha divided by 2. But we also need the other part where we have, like I said, it's always error to the right. So 1 minus the alpha divided by 2. So 1 minus my 0.025, which is going to be 0.975. So we need to find chi-squared of 0.975. Okay, so let me bring up that table. So we have 6 degrees of freedom. I thought I had this hand stability to do that. I'm going to have to do this. There goes 6 degrees of freedom. We need the 0.975 to the right of one tail. And then we need, sorry, I can't see it with my stuff on my screen. This side is 0.025. Because remember, what we're doing, so we're looking at this. Take 95% out of the center, that's going to leave me with a that's going to leave me with 2.5% in each area, right? So we just need that area to the right. Okay. So what we got here is that chi-squared of subscript 0.025 for that area is going to be 14.449. And then the chi-squared for 0.975 is going to be 1.237. Okay, so if I need the confidence interval for variance, it's going to look like this. So n minus 1 times your variance for your sample divided by your chi-squared of alpha divided by 2. So that is going to be this one. And then this is going to be on the other side is n minus 1 divided by times sigma squared divided by your chi-squared of 1 minus alpha divided by 2. This one. So you always want to put your bigger chi-squared here and your smaller one goes here. Okay. So that is going to be n minus 1. So that will be 6 times my s squared is 2,699.865 divided by, like I said, the smaller one goes here, so the 1.237. And then on this side, n minus 1, so that's going to be 6 again, times 2,699.865. All that's going to be divided by your chi-square on that side, which is going to be the bigger one, so the 14.449. So from here, if I just want to have like I said, this is for variance. 6.6999.65. Then we're going to have on this side 1121.129 is less than sigma squared, which is less than 1.233, 13095.546. So you might go, and that's really big for a standard deviation. Yes, it is, because remember, this is the variance. Now, if I want the standard deviation, I just do square root. So square root of 1121.129 going to be less than sigma, which is less than the square root of 13,095.546. So sigma is going to be between the square root of this side is 114.436. If I do the other side, 14.9, we end up with 33.493. So that is my 95% confidence interval for my population standard deviation. Okay. So confidence interval variance of a normal distribution are based on the fact that when a sample of size n is drawn from a normal population, the quantity that s minus 1 s squared over sigma squared follows a chi-squared distribution for n minus alpha degrees of freedom. All right, like I said, we're not going to go too in depth on this. Therefore, for a proportion n minus 1, all possible samples, so all of my n minus 1 sigma squared over chi squared are going to be between your chi squared of 1 minus alpha divided by 2 and your chi squared of alpha divided by 2. So through some algebraic manipulation, basically what I do is I'm going to, it's like, it's kind of involved, but essentially what it is through some manipulation that kind of goes beyond the scope of algebra that we've done really in this course. Going a lot into inequalities. What happens is that if you solve this for sigma squared, what ends up happening is that you're going to end up with sigma squared is going to be between that n minus 1 sigma squared divided by your chi squared for alpha divided by 2. So your bigger chi square here. And then the other side would be n minus 1 times sigma squared s squared divided by your chi squared of 1 minus alpha divided by 2, which is going to be your smaller score. So like I said, like it's much more complicated to talk about than it is our other distributions. What it really comes back to is that this quantity here has to exist between those two chi-square scores. So when you look at this distribution, what we're saying is that if I'm looking at chi squared, and this is 1 minus alpha divided by 2, this side is your chi square of your alpha divided by 2, that somewhere this n minus 1 s squared divided by sigma squared is going to be in this range between here and here. So that's all that's part of saying is it's trying to talk about what that distribution is really representing, and it's representing these scores here. And it's going to put them between these two chi scores. All right, so just one more example. A sample of 30 jockeys, so n is 30, finds a sample standard deviation. So S is going to be 1.5. finds a sample standard deviation of 1.5 inches in their height. So jockeys, ride horses. So they usually stay pretty centralized in their distribution of heights is what this is saying. Assume these values are a simple random sample from a normal population. We want to construct a 98% confidence interval for the population standard deviation. So things to remember here is that look for the standard deviation. But what we have here is S squared and not that sample standard deviation. So you have to make sure that this S gets squared. Okay. So we need to fill this in. So when I talk about my confidence intervals, we got 98% level of confidence. So that means my alpha is going to be 1 minus 0.98 or is 0.02. So if I take half of that, I'm going to get 0.01. So the area to the right of this chi squared would be the 0.01. This one over here, if I look for the area to the right of it, that's going to be 1 minus my 0 divided by alpha, because remember, there's a 0.01 here. So that's 1 minus my 0.01, so 0.99. So we need to switch over to our table so we can figure out what these chi-squares are. Okay. Oops. Gotta get rid of this part so we can see what we're talking about here. So like I said, we need these two chi-squares. So we need the chi-square for 0.99, and we need the chi-squared for the 0.01. And we have 30 is my sample size, so my degrees of freedom will have to be 29. There we go. I was trying to grab this thing and it wasn't coming along. So here we go. Ooh. There's my 29 right here. So I need my 0.99 and I need my 0.025. So as you notice, these numbers are getting bigger because this is what we're dividing by. So it's making sure that we've got larger samples, we should get smaller intervals. So it's making sure that those margins of error essentially are getting smaller. So this is pretty standard for what you're going to see with a chi-square distribution. So for the 99, we have 14.256, and for the 1% is going to be 45.722. All right, so let's go back here. So as we said before, that formula for this is going to be n minus 1 s squared divided by your chi-squared of 1, oh, sorry, chi-squared of alpha divided by 2 square root is going to be less than sigma, which is less than your square root of n minus 1 s squared divided by your chi-squared of your 1 minus sigma squared. So what it is bigger score, smaller score. So we are going to have n minus 1 is just going to be 29 because we have sample size of 30. So this times 1.5 squared, because S is the standard deviation of 1.5, divided by the larger of my chi-squares. So the 45.722. This is less than sigma, which is going to be less than the square root of 29 divided by 1.5 squared divided by 14.256. Right, so just always bear in mind that which we need in there is not standard deviation. We need that variance, so we can't use S as 1.5. We need the S squared. So we're doing a square root of 29 times 1.5 squared divided by 45.722. So we are going to end up with a 1.195 is less than sigma, which is less than, well, we have 14.256, which is going to be less than 2.139. Make sure I run that correctly. Okay, so even though the sample standard deviation was 1.5, what we're saying is that for the whole population, that standard deviation could be between 1.2 and 2.1 essentially. So we vary by about 1.2 inches to like about 2.1 inches.